Okay, so let's move on to the coding part. Um, so what I'm going to do, I'm going to start with the lab one code. So this is a simplified version of what I provided you already in the last lab. So where was that? If you go to the Canvas page and then in the files, every day after the labs, what I'm going to do, I'm going to upload the code for that lab here. So you can see the lab one code is already given here. This is what I did uh, last week on October 5th for the assignment that was due yesterday. Because of the add drop deadline, you have more time, but this is for assignment one. And there was one extra slider which I removed here because I'm not going to use the color changing slider here to make the view more clear. I just removed that slider. So we can start from there. And then I have everything, including the libraries here. And then I'm going to start by editing the code and continue with more of the options. Okay, so again, I'm going to open the code using Atom, since this is our choice, our editor of choice. So this is the HTML part. As you can see, we have the libraries included here. So the matrix library is not added here. What we need to do is to add one more line here so that we have all the 4 libraries. So the matrix library is more about the transformations, which we didn't need for the previous one, but we do have the library, which you modified for your first assignment or assignment 0. Also, there is another version of the clone matrix in the book. You can also use that, but I'm going to use the one I have here. So let me add that here. Actually, let me organize the code a bit better and move it here. And then we have all the 4 libraries included. And now in the JavaScript part. So we already have the assignment1.js. So let me do one more thing just to avoid confusion so that we can use the code for the assignment 2. I'm going to rename this to assignment 2 and also this to assignment 2. So obviously this is not going to run because we don't have the right name in the HTML. So I'm going to open it again. Now it has the right name and open it again. So this is our HTML file and the JavaScript file. I need to change this to assignment 2 as well. So now hopefully this is going to run without any trouble. So you can see this, right? So let me quickly open the console page. I can do it from inspect. And if I check the console, still printing the triangle from my code. That was somewhere here. This one. Let me remove this to clean up the console. I don't want to see all those details. Okay. Okay. So now what we are going to do, we are going to follow some steps that are necessary for the task we have on our hand. Let me type in the steps here just to make sure, or let me create another file. This is just a text document. or I can call this concepts, and then let me add the folder. This is week 3 and lab 1. So from the assignment description, we can see we need to learn these things. So we are going to learn these things here. How to apply transformations. And we are, even though it's called saying etc., we mostly have these 3 things. So we are going to learn each of them. And so these are going to be our primary subtopic for today. And once we know how to do the transformation, as you can see here, we need to do the 2D geometric shape and 3D objects. So we are going to do that. Okay, copy from here. Oops. So we can exclude the 2D because our object is going to be 3D. So we are primarily going to do 3D objects, right? So our triangle was 2D here. Just by making the third, the z-axis 0. So if we make something 3D and then make the z-axis 0, it is going to be 2D. Or we can remove that as well. Both is fine, but since our default object is going to be, so this is called block QNMO, right? So a block or cube is going to be our building block here. That's why we are going to create 3D objects. And so cube is going to be our primary object we're going to learn here. You can do sphere or cylinders, but I'll show you where to find those other objects. So we are going to create a class for the 3D objects. And then we are going to do set up color attribute, right? Because we need to create some sort of color for our object. Finally, we are going to learn how to do the animation, because that is also another requirement for our task. So I want to split that since we have 2 labs. Probably I will mostly cover the transformations and then some of the 3D objects. And then finally, we'll do the animation and color the next week. As I discussed with Professor Davis, that having all of the stuffs in one day may be too much for everyone to watch the video. So the nice thing about the next assignments are they are going to be 2 weeks apart. So last assignment 0 and 1, there was only 1 week to submit. But now for each of the assignments, there are 2 weeks before the submission due date. So now we have more time. You can use that time to complete your work and have a better output. And the nice thing about this, as you can see from the Hall of Fame, there is going to be contests. So the contests are usually happens starting from the assignment 2, and it continues until the last assignment. And if you get a if you are in the first 3 places, that is decided by vote from students, your work is going to be in the Hall of Fame. So that is something you can try try to get by doing a very nice work and get the vote from other people. Okay, so let's go back to our work. So these are the things we're going to do. So let's start with applying transformation. Okay, so right now we have a triangle, as we can see on our screen. We have a color defined for our triangle, that is this defined here, uh, not defined here. So the color is defined outside of the GPU code or the shaders, which we learned in detail in the last lab. And we are passing that color to the shader using this uniform variable, as you can see. Okay, so now we want to apply your transformations, right? And how we're going to do that? So the way the transformation works in OFGL is we can have multiple options of the transformations. You'll see that from the book example. Let me actually try to show you. So they have quite a few examples with how to rotate, translate, or scale triangles. So this is one such example. If you check this one, so they have this red triangle that is translated from the center, right? And you can always view the page source to see what exactly they're doing. So their translation is simpler. They're just using some variable and moving the vertices by adding the variables. We don't want to do that because the requirement for our assignment is to apply the transformation using matrices. So that is like a hard requirement. So even though this is possible just by using some variables, we are going to use that using matrices. So if we go back to the examples, you'll see there is more example. For the rotation, they have 2 examples. So this is one example of rotation. They're rotating the triangle. Again, if you check the page source, you'll see they are using the rotation angle and multiplying that directly to the positions, to the vertices. So this is one way, but again, this is not going to fulfill our requirement of using matrices, which is sort of you need to do to get the credit for the assignment. So this is the right example. They have this rotated triangle matrix. You can see the result is the same, but here, if you check the page source, you'll see they used some variable which is called X-form matrix. So from the name, we can assume they're using matrices here, and they are. And we will do our work similar to this example. Not exactly like the one, because you'll see they are defining their matrices here. We are not going to do that. We are going to use our library function. That is already created inside this cone matrix. Also, they have another example with scaling. If you check this one, you'll see they're still using matrices in the scaling. So using the same X-form matrix, they have a scaling matrix defined here, which is not necessary for our case because that same matrix is also defined in this cone matrix, which they didn't use. But we are going to use that anyway. We are going to take the advantage of having the matrix. Okay, so As we mentioned, we are going to use a matrix. Let me explain how to do that. So let's say we want to translate our triangle. So I'm going to do some annotation here. So this is our axis. I don't know how straight that is. Then let's say this is our y-axis. This is our x-axis, right? Hopefully this is a good approximation. Then, so let's say we want to translate our triangle here, maybe around this x-axis. So this is 1, right? And this is -1, and this is -1. This is 1. So this is our x-axis. This is our y-axis. So if we want to translate our triangle from here to, let's say, 0.5 to the left, then we need to apply that translation using a matrix, right? And for each of the transformation, the matrices are defined in the book. Also, they are defined in our library. So for translate, the matrix is going to be something like this. So you'll see that in the book also. Also, they have one good example. They have many other examples. So we need to use an identity first. So this is going to be our identity. And then, so this is a 4D matrix because we are going to use homogeneous coordinate system. So this is going to be our last column, and this is going to be 1 to validate that column. And these are the value we are going to use for the translation. So the 3 axes, right? Let me erase this one and draw it again. So this is our translation matrix. Now, what if I want to translate this triangle using this matrix? Okay, let me also show you how to translate matrix. We need not the 2D matrices, we need 3D matrices. So there should be some example. Let's check this one, what they're saying. Not a very good example. So the book have better examples of how to use the translation matrix. Let's search for 4D. I hope they had better examples, maybe. So yeah, they have some simple projections here. So this is the identity and more detailed stuff that you'll learn later. So the thing is, if we want to translate our triangle, then we can multiply each of the vertices, and the result will be the translated result. So how did we define our triangle? So in our code, we defined our triangle using these 3 vertices, right? So what we need to do, each of the vertices, let's say V1, V2, and V3. So what we need to do, we need to translate each of these. So this is our translation matrix. So translate V1 by multiplying that using this translation matrix, right? And the result would be the new vertex that is going to be, let's say, V1 bar, right? So that would be, let's say we want to translate by 0.5 around x-axis. So this would be 0.5 and others would be 0. You can have translation on multiple axes. So you can have translation around x for 5 points, also y for 5 points, and the translation would be along this path, not this path, this path. And then you have to just make this one 0.5. But let's keep it simple for now. So, but we need to translate all the vertices, right? So TV2 and then V3. So this will give you a new triangle. And once you define the translated vertices, the rest of the task will be done inside the shader, right? So the shader will draw the whole translated object for you. That can be 3D or 2D. Similarly, you can do, so this was translation. Why don't I type? That would be easier, right? So this was translation. We can also have rotation and scaling, right? So we can have rotation and scaling using matrices. So you just need to define similar matrices for each of them. So for example, rotation can be a matrix R, scaling can be a matrix S. And that matrix is something you'll see covered in the lecture, right? That will be covered in the lecture. But I guess we can see at least that example from the book code we have. So if I go back there, okay, the screen is too much. Probably I should have used a whiteboard. Let me show you. Maybe it would be on the other side. So if we check here, chapter 3, and see the rotation with matrix, then view the page source. Actually, let me inspect the page. And here we'll see a better source. So the source is WebGL. Then we have this chapter 3. So this is a rotation matrix, right? So this rotation is done by using this matrix. And for the scaling, they're using a similar matrix that you can see here. This one, right? So as you can see, Sx, Y, Z, you're using 3 variables, and then each of the variable is going to scale the object by multiplying with this value. So if this you make this Sx2, it will scale along x-axis by 2, right? We'll see more examples like this. But this is our main concept, how we are going to apply the transformation. And how we can apply multiple transformation, what we can do, we can combine all the matrices in a single matrix like this. That would be Let's say this is the final matrix where we'll have all the transformation. Here we can multiply in the rotation matrix and then the translation matrix and also the scaling. And we are going to use the right sequence. So rotation, translation, and scaling. You'll see in the book they explain which should be done first and why. But this sequence is really going to be important for our task moving forward. Okay, so enough about these background concepts. I'm going to clear the screen and we're going to write some code. So clear all drawing. So let's start with the translation here. Okay, so how we are going to do the translation? We are going to add our translation matrix, right? And that is going to be done just after the buffer. Right? So here in the buffer, we defined how to draw the triangle. So that once the triangle is drawn, now we can start saying something about the transformation. So let's say transformations. Okay. So the first step is going to be defining a matrix, and that is done by let me create a matrix. To make it simple, first I'm naming it using the transformation operation I'm going to do for this one. So first thing I'm going to do a translation. So I'm going to say translate M. M is for matrix, right? And then I'm going to define a new matrix. Okay. So I am going to define the matrix as an object and where the object is coming from. So now we need to take a closer look at this, the class given here. So you can see in this Kuhn matrix, if the original version from the book or the modified one, we have these classes. So this is our vector3 class that was used a lot in the assignment 0. Then we have this vector4 class that can also be used for vectors, but you can see we don't have other functions here. But we have this class called matrix4. That is what we're going to use a lot for our transformation operations. So as you can see, the matrix in the constructor, a identity matrix is defined here. That is going to be our starting point with any matrix. We can also call this set identity if we need it later, but by the constructor, we're already setting up this identity. Then we have other functions like multiply vector, 3, 4, transpose, set inverse of, many others, set ortho. But the ones we are going to use here are the transformation matrix. So you can see we have this set scale. And if you look at the matrix, you can see this is pretty much similar to the example I showed you from the book. So we have X, Y, and Z. So this is the matrix. These are the elements. And this value is coming from the parameter passed by the user. So if someone wants to scale along the x-axis, they can just pass the value here. Or y-axis, they can pass the y value here. And z-axis, they can pass all three values if they want to scale it around all axes. And this is the set scale. And there is another function that is called scale, right? And so this is going to define the scaling matrix. This is not going to define a matrix. This is directly going to multiply the values. So we are going to use the matrix. So we are going to use this set scale function for our work. Similarly, there is this set translate, which we are going to use now. And you can see the format of the matrix is similar to what I just showed. And then we also have set rotate, where you can rotate something using this angle alongside some axis, X, Y, or Z. And the axis you want to use for the rotation, you just make that axis 1 and make the others 0. You can you can rotate around multiple axes, and you can make both of them or all of them 1, and then the angle will apply to all of them. We'll see some of those things, but this makes more sense for 3D objects. For the 2D triangle, it will not make that much sense. And then let's use the set translate first. Okay. So what I'm going to do is, for this translation, going back to the code of the JavaScript, and I'm going to use a new matrix. So the first thing is to define the object, right? The one we saw here. So everything is part of this object. So part of this class. So first thing is to define the class, define the object of that class. Okay, so new matrix 4. And as I showed the constructor, it is going to just set up the identity matrix, right? And let's try to print the value of the matrix. So I'm going to do translate M and print everything first. Okay, so if I run the code, you'll see it is printing the matrix 4 with a lot of things. And the elements are this identity matrix. So if I change the code to just print the elements, then it will only show the elements. Okay, now we have the elements. We are going to apply our translation. So it is moved by the specific value we want to move the triangle with. Okay, so for that, what I'm going to do is I'm going to apply the translation to the matrix, right? So we have this new matrix, we have this translate M. What I'm going to do is translate M, and then I know the right function we have here. Set translate, copying that function. And we need to apply the exact value we want to use. So from our definition, we know that we need to pass X, Y, and Z. Then I want to translate alongside X by 5 points, right? So I have this 0.5 and then 0, then 0. Okay, so I applied the set translate with this matrix, but that is not applied to the triangle. So if I refresh the code here, it will not have any effect here, right? Because it is not applied in the shader yet. Okay, so to order that in order to apply that to the shader, I am going to create a new variable here. As you can see, we had this attribute variable for our positions. We want to apply the translator for translation for each of the positions, right? So somehow I need to apply that here. And in order to apply the matrix here, I'm going to create an uniform variable here. So if I remind everyone about the uniform variable, so we have three types of variables in the shader, right? So the attribute variables, the uniform variables, and the varying variables. So the attribute variables, they are already predefined. You can use them for defining the positions or colors. Uniforms variables are something that we can pass from the CPU side to the GPU side. So we want to pass the matrix from the CPU side to the GPU side. That's why I'm creating this uniform variable. And this uniform variable is going to be a matrix, right? A mat4. And let's say, following our naming convention, as I mentioned, attribute variables are, we have this prefix a underscore. And for uniform variable, we're going to use this prefix u underscore. So let's give the same name, the one we gave our matrix here. So I'm going to copy this and then apply this here. So we're going to call this u translate m, right? And I still don't have the matrix passed here. I will have to do some extra steps for that, right? And also, I need to apply that to each of the positions. If you remember from the figure, the annotations I did on the screen, I need to apply each of the vertex v1, v2, v3, which is passed using this a position with this matrix, right? So I'm going to apply this multiplication here. Okay, so this is a mat4, right? And in order to multiply, we need a vec4. So I cannot multiply with this 3D a position. I need to multiply it with this here. So our u translate m is a mat4, and this is a vec4. So this operation is going to work, right? Because we need to be careful about the size of the matrix and what we are trying to multiply with. So that the dimensions are going to be match for both of them, since this is 4 by 4 and this is just a 4D vector. Okay, so if I run this, there is not going to be anything, right? Because I'm trying to draw something, the shader, which is not defined yet. So we don't have this. This is blank. I need to pass that here, similar to the way we pass the color. And how can I do that? I'm going to create another variable like this u color. So as you can see, we had this u color in the GPU side and another variable with a similar name. And then we passed the uniform variable using this function. So we have something similar for this one as well. I am going to create a variable called u translate m, since it is the name there as well. Usually we try to keep the same name for the JavaScript side and the shader side. And then we are going to do a GL uniform location similar to this one. Actually, I can just copy this and then replace this with the name I am going to use here. So now this u translate m and this u translate m, they're connected. And I have a line of communication between the shader and the JavaScript code, right? So you can consider this as a communication channel between these two. Now I need to do something similar. So this uniform variable was we passed 3 floating point variables. We had the option to pass the vector using 3v, but we chose to use the 3f. That is not going to work for this one, right? So we need a separate function that is similar, but the format is going to be different. So this is going to be uniform, except now we are going to use uniform matrix for FV. So uniform matrix for FV. So this is a matrix 4, and F is for float, V is for vector, right? So if you check this function for WebGL, there are two versions, OpenGL and WebGL. We want to see the WebGL version. So it will show you some examples how to use that. So we need the location where the matrix is going to be, the value, and if we want to do a transpose or not, which is for our case, it is going to be not. They have one example here. This is similar to, this is a 2FV. Ours is going to be a 4FV. So we need these three things, right? Okay, let me copy the whole thing from here and then. So where is the location? So we got the uniform location here, right? So I know this is my location. So copying that. Do we want to transpose? No, we don't want to, right? So I'm just going to say no. Using a Boolean, false. And we need the value. So where do we have the value? So the value is defined here, right? Where we did the set translate. So this is going to be our value. So the value is a matrix, but we don't want to pass the whole class. So this is the whole object. So this is the whole object, right? We only want to pass the value, which is going to be the elements. Okay. So now if everything is correct, if I didn't make any mistake, if I try to run this, there should be something on the screen. Yes, this is, fortunately this worked. So we have our translation done, and the translation is alongside x-axis. So let me try to make maybe translation, multiple translation, right? So this was 0.5 here. What if we want to do 0.5 here and 0.5 here along y? So that translation would be like a 45-degree path here. So let's do this 0.5. We have nothing on z-axis, so changing this value will not make any sense. So this worked, right? So we can do this translation any direction we want to.